Hi, everyone. I'm Jamie Peterson, Director of WolframU. 3 weeks ago, we launched version 15 of Wolfram Language and Mathematica, and today we continue with our new in version 15 webinar series. Today's session is dedicated to what's new in visualization, graphs, and computational geography and astronomy. Joining us today are Wolfram senior developers Brett Champion, Jaebum Jung, and Jose Martin Garcia. You'll want to read Stephen Wolfram's release announcement for his comprehensive coverage of new version 15 functionality and his philosophy for applying computation in the world of AI. The blog has several sections that cover functionality you'll be seeing today. And here's some about the geography and astronomy. To try the examples from today's presentations, you'll want to access version 15, and we have a free trial offer so you can get started right away with Mathematica version 15. I'm going to ask a poll question to the webinar audience now about whether you've already upgraded to version 15. We have a YouTube live stream audience as well, and for those of you on YouTube, feel free to type your responses, comments, and questions in the chat. We have Wolfram webinar and technical staff joining during the live stream to help us coordinate Q&A. So I encourage you to type your questions as we go along. A download link with the webinar presentation notebooks appears in the pinned note at the top of the chat panel. That's in kind of that greenish, light green color there. That download link has notebooks for all the presentations today. The chat and Q&A areas on the right of the screen are where you can submit questions as we go along, and where you can read the published Q&A. Finally, make note of the full screen toggle available in the top right corner of the presentation window in case you want to make the shared presentation area full screen. We hope that you'll join us at the upcoming remaining sessions in our series. And you'll want to check back with us to download the notebooks that apply to those presentations. So thanks for your attention. Without any further delay, I will pass things over to Brett to begin with today's presentations.
Thank you, Jamie. So today we'll be talking about some of the new features in 15 for visualization, the plots and charts. There's not enough time here to cover absolutely everything, but these are the key points. And let me just get the share going. There we go. So the first topic we're going to talk about really briefly is updates related to the new time series. So as Rob Knapp and Gosha Strabanska discussed in a previous episode of this series, time series and event series in version 15 have been updated to use a lot of the same underlying technology and frameworks as tabular. And from a visualization standpoint, this means that, well, I should say that, and one aspect of that is that time series and event series can now have named components within them, and when you have multi-series of various forms. And similar to tabular, where we introduced a arrow-based syntax, a rule-based syntax to indicate which columns you want to visualize, the visualization functions have picked up an arrow-based syntax to specify which components you want to visualize. So here we have a date list plot, and we have one of the new time series. And if we look at the preview, okay, the preview didn't magnify, so we'll just hide that again. So there's 4 components in this time series. Hasbro, Mattel, Disney, and EA, all entertainment companies. And we're going to plot the time series corresponding to Hasbro and Disney using this arrow mechanism, and then we get sort of the corresponding plot. The details of the syntax, what goes on the right-hand side of the arrow, varies a little bit between time series and tabular, because in the case of time series, event series, you always have that time axis sort of present that you're plotting against. And so you don't need to manually specify that like you would have to if it was in a tabular input. The other change that we made relating to time visualization and time series is we've changed the default setting of the joined option in several of the viz functions, so that if you're plotting a time series, it's a joined curve. If you're plotting an event series, it will be discrete points. And so here I have an event series of how many goals my favorite soccer team scored last year per game. And so, a couple of high scoring games, 7-2 loss and a 7-1 win about a month later. But, these are, this first plot was dateless plot of a time series, and it's a joined curve dateless plot, same function of event series, and these are, because it's event series, it's doing it as discrete points rather than, say, trying to connect them as might have been done in a previous version. Moving on, the next big change is that several of the chart named options were switched over to plot named options, so that there's a slightly smaller set of symbols that you have to really remember. So chart style, which has been around since version 7, has been migrated into plot style. Similarly for chart labels and chart legends, going into plot labels and plot legends. In the simplest cases where you're just saying, I just want to specify a particular color or style, it's just a name change. If you have just a single data set, it's also still just a name change. And so that's sort of really easy, and this applies to basically everything that has a chart in the name. So bar chart, pie chart, bubble charts, so on and so forth, the 3D versions. So where there's a little bit of a divergence is when there's multiple data sets. And so in that case, previously with chart style, if you gave a list of styles, it applied those styles to the elements in the first data set, and then to the elements and those same styles again in the second data set. So red, orange, yellow, got repeated in each of these groups. With plot style, it now applies per group, similar to what happens in, say, list plot. And so when I change the plot style, I get a red group and then I get an orange group. And chart style had a nested list construct that allowed you to specify if you wanted the group coloring or the element coloring or some combination of the two. And in the case of the new plot style, that's being done with an association syntax. And so I can say, I have plot style goes to my association. It has an elements key where I give my list of styles, and then those list of styles are applied sort of at the element level. And the keys that are present vary a little bit by function. All of the chart family sorts of things are generally going to have elements and groups as the keys, as well as a base key for doing an overall style. And this has been applied back even to like the functions that always had plot style as an option, say. And so here we have plot of 2 curves, and I can say plot style goes to my association. Here I'm using the base to change the thickness of all the curves. And then in the case of plot, functions is the key that says, what is the list of styles I want to apply per function on a function by function basis. And I really like the base thing here because then I don't have to sort of figure out how to map turn each of these colors into a directive, combining the color and doing a little bit of programming to get all those set up. I just specify the parts that I want. And so moving on to a completely new function in version 15, we have categorical histogram. This is kind of like histogram, but for categorical data. You could think of it also as a streamlined version of bar chart of counts of your data. And so here I have a data set with, I think, 1,000 fruits. I mean, not 1,000 different types of fruit, but 1,000 instances of different types of fruit. And so you see peaches and grapes and mangoes and whatnot, and we happen to have the counts here. And as an aside, I'll mention that it's not required, but in this case, I'm using the new nominal objects to represent the fruits. And so that's why each of these has a little background and a little marker underneath it. And so nominal is just a way of saying I have a collection of things that I want to think of as categories, and it knows sort of what the set is and what the element in that set is. And so if I take my data and run it through categorical histogram, then I get my set of bars. And by default for nominal data, for unordered data, it's going to be sorted from most common to least common. And the second argument of categorical histogram is going to control sort of how many bars you see and how you see them and whatnot. In normal histogram, you would say how many bins you want or how wide you want the bins to be. That sort of thing is in the second argument. Here, it's a little bit different, and that's why we have a new function and not just say histogram of the data with a scaling function set to a categorical setting. Is we wanted sort of the second argument, the controls, to be really specific to categorical. And so here I can say that I only want the 5 most common elements, and so I just get apples through kiwis, these first 5 bars out of the entire data set. I can say that I want to see all the bars, all the categories that occur at least 50 times. And so in that case, it's going up through peach, which has 71. And if we look at whatever was after peach here, which was cherry, that had 46 or 48. We can also control to some extent what the ordering is for these nominal ones. So if I want to sort the categories alphabetically instead of numerically, I can go from apples up to peaches and see them that way, depending on sort of whether you want to have a workflow where it's easier to find what a particular fruit is and see what its count is, or if you want to see sort of what the most common is and least common. And the second argument has a lot of flexibility of how many bars you want or how you select the bars or what the ordering is, that sort of thing. And we also have ordinal as a new categorical object. And this is very much like nominal. The difference is that ordinal has an ordering in it. And so here we have some temperatures, which are just set as hot, neutral, sorry, let's go in sorted order is cold, cool, neutral, warm, and hot. And you see if I do the categorical histogram of that, we get the categories in their order, in their ordered order, in their sorted order, rather than most common first. I mean, in this particular data set, it happens to be that the largest one is first, but then after that, it's no longer in decreasing order. So we also did a pretty big update to distribution chart, which was one of our statistical visualization functions from probably about version 8, I think. And previously it had a lot of flexibility in what it could generate, but that lived in a chart element function. And we decided to move a lot of that functionality into a second argument. And it also got some aesthetic changes along the way. So if you haven't used distribution chart before, it takes sets of data and shows you the distribution of each data set, sort of next to each other. So it's a generalization of a box whisker plot where you have multiple box whiskers. And by default in version 15, it's showing a one-sided smooth histogram. Previously, it showed a two-sided smooth histogram, and that's still available by using violin as the second argument. There are several named settings, named appearances in the second argument. So we can do a normal binned histogram. And one of the things that was an improvement in version 15 is that when you do this, all of these histograms have the same sort of bin width and binning specification. And so, at least by default. So you can see that going left to right, everything is matching up. I can modify the histogram, so I wrap a list around it, and then it takes an association of parameters. In this case, bins is saying that I want a bin width of 0.25. This is basically the same argument structure as the normal. It's the second argument in a normal histogram, and so by making the bin width narrower, I get more bins. They're still going to line up as you go across to sort of compare these things. I can change the alignment, so I can have my baseline for my histograms on the right-hand side instead of the left-hand side. If you notice, there's a tooltip that when it shows up when you mouse over this. It has always had that tooltip. The tooltip got a little bit of a style update in this version, using a little bit of what we learned from sort of how we want to format numbers and whatnot in tabular. A different approach for distribution chart is we can show it as a density. So this color density, the yellow color density, is sort of the same smooth histogram levels as what we saw originally. And then we're also saying that we want to show the points on top of the curve so we can see where all the data actually is and see that we have the strongest yellow where we have the most points, and then they sort of the gradient fades out as the points get farther apart. The point width here says that we want all the points to be sort of in a single column. If you make this a little bit bigger, then you'll get some jittering and the points will separate. And then the last function I want to talk about is plot grid, which is a function that takes several graphics or plots and puts them into a grid, similar to graphics grid, but in a way, but has functionality to automatically align the scales within rows and columns in various ways. And so I have a set of plots here, and it's sort of a little bit hard to see here, but like this first plot has a y range that goes from -1 to 1. The one after it goes from -2 to 2. This one has an x range that goes from let's say let's look about 3 to 9, and the one after it goes from 1 to I think about 7. So the ranges are all over the place. And if we put them in plot grid, what happens is we get a nice thing. We don't get all the interior axes and frame ticks on every panel in this plot because so like this first row, these first three plots have been synchronized so that even though this first one only goes from -1 to 1 and the second one goes from -2 to 2 and -3 to 3, they've all been moved to have the same -3 to 3 scale, so that everything will line up. And this axis here applies to all three of those plots. And similarly, this axis applies to all of these plots. And what you might notice is that this first column goes from 1 to 7, the second one's going from 2 to 8, the third one from 3 to 9. If I use all as the second argument, then what it's going to do is it's going to have everything use the same Y range, everything use the same X range. And so all my Y ranges go from -3 to 3, all my X ranges are going from 1 to 9, and you see that we get a little bit of extra space on the right-hand side where the data only went from 1 to 7, a little bit space on the left and right in the middle column, and extra space on the left um, for this. And so this is sort of sharing as much as possible. Um, on the flip side, we can say none and have everything have its own scales, in which case you aren't sharing any axes, but everything will still line up in terms of what's inside these frame edges. And you have sort of full control over being able to say, okay, I want my columns to vary in one way and my rows to vary in the other. So I want, you know, all my rows to have all my y-axes to be the same, but my x-axes to only be consistent within each column. Um, the other thing that I think is interesting and is sort of an important feature of plot grid is how it deals with various forms of like aspect ratio. And so the default setting for graphics is that aspect ratio is automatic, which means that a particular visual distance so the visual distance used to represent one unit in X is the same visual distance unit that's used to represent one distance in Y. And so if I say create a graphic of some random walks where everything is moving in, one step to the right, one step up, one step left, one step down, and you're doing that sort of walk, you see that you end up with everything is on a square grid. I mean, the size may vary based on like how far they got in various directions, but everything's on a square grid. And when we do a plot grid of this, that is respected. And so everything here is still square grids. We'll turn the frame ticks on. You can see that a lot of these got a lot of extra space. But like the distance from 0 to 10 on this x-axis is the same distance visually as from -10 to 0 over here. -10 to 0 over here. That's all the same distance in terms of screen space. And if I say all, then it will go even further. Everything gets the same plot range. So it goes from like -40 to almost 20 in the X range and about -15 to 10 in the Y range. And so it's laid everything out, but not distorted anything. It's added extra space, but what was square is square. If you had circles, they'd be circles. So if you're doing those sorts of environments where the visual appearance of things is sort of really important in that aspect, that will be preserved. So now I'm going to look at the Q&A a little bit and see what answers I can, or what questions I can answer quickly before handing over to JBum. Okay, so an important question. With the name change from chart style to plot style, etc., does it mean that the previous code will not be accepted anymore? Absolutely not. So, I mean, if we go back up to that slide, you know, I reevaluated this notebook, a little bit before this talk. Everything is, these comparisons were bar chart goes to standard, with chart style, bar chart with plot style. If I make this standard green instead of standard red, that still works. We didn't break anything. It's just, plot style is the preferred thing. Chart style will still work, absolutely. We're just not encouraging the use of chart style anymore, but you totally do not have to go and change your code. Question about how I got the iconized directions. And then so let's, okay, I did that a lot in this notebook. And so all this is how did I get this? So for people who maybe aren't entirely aware or aren't, because this is a relatively recent feature, this is an iconized input. It formats as this little gray box, and in this case, it just evaluates to a list of these numbers. Normally, if you do iconize of something, it auto determines what this label is going to be, and this is a list of things, so it just did list ... If you put a thing here, this is what will be used as the label. So I just iconized my list of numbers to be using here because it took up less space and wasn't really an important part of the example. And let's see. Can you add annotations with plot grid like ABC, etc.? Not automatically at the moment. That would be a really cool feature for doing captioning and whatnot. And it's something we're thinking about but haven't gotten to quite yet. What is the meaning of the gray bar and vertical tick drawn under the categorical date boxes? Okay, so that is categorical histogram. So for nominal data, for nominal categorical objects, we have what the category is in this. Let's magnify this just for. We'll make that really big. So I'm not sure if the blue bar is actually supposed to be here. So this is an indication that this is a categorical thing and not some other thing. If I had fewer categories in this set, so you may not see it, but there's a tooltip on this that says that the categories are apple, banana, cherry, ... There's some number of them. If it was a smaller set, you would actually see discrete bars here. And in the case of an ordinal thing, let me go, where'd that go? There's the ordinal one. Is this responsive to font size? Not the way I want. We'll make those bigger as well. right? So A, this is a small enough set that you see those discrete bars. But in the case of ordinal, this blue bar actually tracks, within the range where that ordering is. So cold is the smallest, then it goes up to cool, then neutral, and then warm, and then up to hot. And so it's the bit underneath does two things. A, it helps you to understand whether it's A, that it is a categorical object, and B, whether it's nominal or ordinal. And in the case of ordinal, it gives you a little hint of where in the order you are. So I think that's where I'm going to stop my presentation. I'll continue to look through Q&A and see what things I can answer relatively easily in text. But now I'm going to hand over to JBum to discuss improvements in graphs and networks. Thank you.
Okay, hello everyone. Thanks for joining. I am Jae-bum Jung and I work in algorithm R&D at Wolfram Research. So today's session covers the graph theory segment of our webinar, focused on new features I developed for version 15. There are three key features I'm particularly excited about, and I will start with a quick overview of what they are, and then we will dive straight into examples. First, graph value plot, which turns graph values into a finished visual in a single call. Second, tagged nest graph, which builds a graph from a rule and keeps the history of how it grew. Third, the styling side, plot theme and graph highlight style for instant polish, plus the cleaner way to draw your own vertices and edges. Let me start with graph value plot, because it's the one I reach for most often. So graph value plot, so here on the left is the ordinary graph, and on the right is the same graph, but I have asked graph value plot to show me page length centrality. Notice that I never specified a size, a color, or a scale. I just named the measure, and the function did a visual encoding for me. The design goal was you describe what you want to see and not how to draw it. So let me put that on a network where it actually tells a story. So this is a real social network of dolphins. And the value here is page length centrality. The most connected, most central individual are immediately the ones I land on. So I did not build a legend or sort a table. The provenance is the answer. So I notice the default is doing more than one thing at once. So it scales the vertices and shade their color together. And also it quietly grays the edge specs. So the nodes carry the message. That automatic choice is usually what I want for us to look. So, but sometimes I want to pick the encoding myself. So let me show what that looks like. So here I take single measure, the between its centrality, and ask graph plot value to encode in three different ways. So on the left, the value drives node size. In the middle, it drives color. And on the right, it drives opacity. The underlying data is identical in all three, but just only the visual encoding changes. So I choose encoding that fits the story, like size naturally leads as importance, color leads well in print, and opacity is good for letting keynotes emerge from dense background. So this flexibility is something I wanted to build in from the start. So I'm making it explicit. And here's another concrete example. And it shows that edges carry values just as naturally as vertices. So this is small railroad network between Canadian cities, and each line has a capacity, the daily number of car compartment it can move. So I pass the graph and the name edge capacity. And graph value plot read that property and turns it into edge styling. So thicker, more solid lines for the high capacity route, and thinner and fainter for the small one. So like here, thicker and like thinner. So the busiest corridors are obvious at a glance, straight from a property that was already on the graph. So again, I did not compute anything or build a legend. The capacity was sitting on the edges and the plot surfaced it. So next, the quickest way to feel how this works is to change the value live. So let me make the interactive for a moment. So this is one fixed graph. And the menu chooses which measure graph value plot display. So as I switch from degree to between is to page length, the emphasis moves around the graph. So because each measure tells a different story about the same structure. So this is the loop I want in explanatory work. So pick a measure and see it immediately. Try another and all without the rewriting any style. In a notebook, this is a single manipulate, and it is the best way to find a view that actually answer your questions. So, and next, then when you have your own numbers instead of built-in measure like this, the workflow is still identical. And let me show that. So the values for graph value plot doesn't need to be the built-in measure at all. So here, I hand graph value plot a plain list of numbers, one per vertex, and style it like the graph the same way I did before. So in practice, those numbers might come from your own model or simulation or like external data set. And the function does not care where they came from, so which is exactly what I wanted. But not every value I want to show is a number. So let me bring categories into the picture as well. So the values so far we've seen have been continuous numbers, but graph value plot also handle categories. So here the example, this is the network of American college football games, and each team carries a components annotation. So notice that the value is a string, the component's name, and this is not a number. So I pass the property straight in to the graph value plot. And with a discrete color encoding, each component gets its own color. And with a shape encoding, each component gets its own markers. So teams in the same component snap together visually, which is exactly what I want for labeled grouping, like categories, or type, or membership. So that is the full range I designed for numbers or categories, vertices or edges, or built-in measures or your own data. So now let me switch from measuring graphs to building them. So now to the tagged nest graph, which I added to build a graph straight from a rule. So I give start point and a step, and this function apply the step over and over, also recording the result as a graph. So here's the step takes a grid point to its four neighbor. So from a single point, the structure grows outward and you can watch it expand across the three panels. Like this is first step and two steps and three steps. So what makes this more than a drawing is that the connection records how each point was reached, not just where it ended up. Let me take a simpler numeric rule and look closely at what is being recorded. Okay, let me zoom in one rule to show that tagged really means. This rule sends each number to two successors. So one branch doubles it, and the other adds a square root of 2. The important part is that every edge remembers which of those two operations created it. So doubling step and the adding step stay distinguishable. And I can follow any vertex back through exact sequence that produced it. So for example, like 16, if you go back from 1, it's just using the left rule 1, 2, 3, 4 times to reach this vertex. And then here, 2 plus 3 square root of 2, if you follow it from the start, in using 1, 2, second rule, and second rule. So this is how you see the step that recorded in this graph. So this is why I call it tagged. So graph is not just the final shape, it is record of the process, and I can call it. Then, so because it is a record, small changes to the rule are easy to compare. So let me do that next. So these three graphs use the same depth 3, but these three closely related rule, the shapes diverge almost immediately. It's just three simple rules. Have two left and right rules. So I found this is the most convincing way to show that small change in a rule is not a small change in the behavior. So for example, you got the three totally different graphs with, it's just some addition or minus or multiplying. So very simple rules. So when I am explaining a generative process, putting the variant side by side make the consequence obvious to everyone in the room. So also, and because each of these are real graph, I can do more than just look at it. So let me show the concrete application. So here is where I actually reach for this. So I take the update rule of a small system. So each system maps to two orders by modular arithmetic. And let the tagged next graph explore every reachable state. So because the state repeat, so it's modular, right? So the result is not a tree, but real network with cycles. And it is ordinary graph object, not graphics. So I hand it straight to graph value plot and size each state by its degree. So I'm just using vertex degree measure. So this immediately shows the state that act as a hub, like this 3, 7, 9, and 1. Nothing special bridges the two features, generation product of graph, and every graph tool just work on it. So that round trip from a rule to analyze a graph is the part I'm most pleased with. So now next to the style. So plotting, it can give coherent finished look without touching the low-level options. And I added 2 new plot themes that pair especially well with tagged nest graph. So one, this is frame labeled. So this is on the left. So basically it's just giving the frame over the vertices, also giving the vertex labels with nice styling. On the right, this is circle labeled, same thing. It's labeled with vertex name, and then giving the frame around it with nice styling. So the plot theme set the overall look. So when I need a specific shape, and so I can now draw it myself more clearly. And this is like a smaller, but generally useful edition. So when I draw my own vertices or edges, the shape function, the custom shape function, now takes named argument. So I no longer have to remember slot position. For example, on the left, the vertex shape function, the receive coordinate and size by name, so like a sharp coordinates and sharp size. And I use them to draw the pentagon at each vertex scaled to its size. On the right, I just using edge shape function. And this receives the edges coordinate. And I draw it as a thick dashed line. So in addition to this, there is also vertex argument, which is like a sharp vertex. And the edge argument like sharp edge. So that gives the edge itself or vertex itself. So I can style each element from its identity. So the code now read the way I think about it, like draw this shape here at this size, so which make custom graph rendering much less fiddly. So people, you have to like a sharp 1, sharp 2, and remember what sharp 1, sharp 2 mean. And the last styling tool is about directing attention without redrawing anything. So version 15 had a family of new highlight styles. So for example, like here, I added 5 new highlight style. First one is halo, puts a soft glow around the highlight, and then shadow. This shadow lift is forward with a drop shadow. I can see here. And shadow blue is kind of same to shadow, but in blue. And also you see the background. I mean, your face is kind of white. And then the black shadow, not black shadow, even the simple black is just mostly restrained. It just marks the highlight in just clean black with the white in the face. And black shadow, the last one, is the combination I reach for most. It draw the highlighted part with the blue shadow, like you see here, and render everything else in simple black, using the simple black, actually. So the focus and the context are styled in one consistent path. So, and this tool combines well with others, which is where I want to finish. So this brings the segment together on the Dolphin network. So first I highlight the 5 most central individuals with black shadow so that I know where to look first. Basically, let me also showing what it looks like actually, right? So this is the just highlight with the black shadow. And then I grab value plot to additional thing, like encode the full centrality measure across the whole graph. I mean, and then I just choose the vertex size encoding. So the highlight say start here, and the value plus set, and here is the complete picture. So this last the figure carries both the focus and the evidence, which is exactly what I want to when I present a result. So to summarize, the graph value plot turns a measure property or your own values into a styled graph in one step across many encoding like size, color, opacity, shapes for both vertices and edges. And tag the next graph, build a graph from rule, and keeps the history of how they grew. And the result is just ordinary graph you can analyze. And the style size, the style side, the plot theme, graph highlight style, and named shape function make the result clear and presentation ready with very little effort. So together, they shorten the distance between an idea about graph and a graphic you can actually show. So this is what is new in graph in version 15. So thank you again to attend the talk. And if you have any question, feel free to leave in the chat window. Then I will answer as much as possible.
Jaebong, can you hear us?
Yep. So let me see. I have a question from David. Graph highlight style is a nice feature. Can one do anything similar in, say, plan list? I'm not sure what plan list mean. If you mean by list plot, I don't think there is something like highlighting list plot, but there are another option you can use, like plot style or plot theme. Not exactly highlight.
There's plot highlighting, but it's not exactly the same.
Yeah, exactly. Yeah, plot highlighting is the option, but not like graph highlight style. Any? So if there is no question, then I will just hand over to next presenter, Jose, and he will talk about new in graph and astronomy.
Okay, thank you, Jaban. I'm going to share my screen. Okay. Okay, so hello everyone. I will be talking about what's new in Wolfram 15 about geography and astronomy. And let me start with a little summary. I will be talking about 4 different things. First, I will talk about a new option or a new pair of options in geographics, GeoAxis and GeoAxis Origin, that will help understand what projected coordinates are and how they differ from the traditional unprojected coordinates for latitude and longitude. Then I will talk about extensions in some of the geoprimitives, night hemisphere, day hemisphere, and day-night terminator, that has been extended in a few ways that I will explain. And then we will move on into astronomy, and I will discuss a new function that's very useful to find eclipses for a given location, and then the beginning of our system to work with orbits and in particular, this time with orbital elements. So I'm going to turn off my camera to save bandwidth now. Okay. So let's continue and talk about geo-access. So this is an option that we hope will help explaining the difference between projected and unprojected coordinates, which is something we have seen confused some people. So let me start by taking some common options. In this subsection, we will be working with the Mercator projection. We will be using maps of the whole world. We will be using this vector background, which is a background without labels. And this is the size of the maps. So we have these two maps. And notice that this map activates axis. So we have this axis, while this one activates geo-axis, which is the new option. Here we have longitudes from minus 180 to plus 180. And we have this coordinate, this vertical coordinate, which also goes from minus 180 to plus 180. So obviously this is not latitude, right? So what is this? This is the vertical projected coordinate, and it has the same range here, and that's why the map is square, right? So this is just a coordinate on the square that is this map. Well, here in this new option, we have again minus 180 to plus 180, but here we have true latitudes, and you see they are given in steps of 15 degrees, so 15, 30, 45, 60, 75, and you see how they increase, because this is a property of the Mercator map that it stretches the vertical direction, and in fact the pole is mapped to infinity. So there's the space from 75 to the pole is infinite. So you can compare both cases, and of course Wolfram language allows you to work in both coordinates. For example, imagine that you want to draw a line from the center to this corner. Well, in projected coordinates, that's trivial. We say draw a line, a red line, from 0, 0 to 170, 170, right? These are projected coordinates. And here we have the line. If we had to do it with projected coordinates, we can do it. Sorry, with unprojected coordinates, we can do it. We would have to use geopositions. The geoposition 0, 0 is the same, but this geoposition is now difficult to estimate, right? We would have to use, I don't know, latitude 80. It would be more or less here, but obviously this is like 83 or something like that. So depending on what the problem is, depending on what you want to do, it's easier to use projected coordinates or unprojected coordinates. And now axis and geo-axis allows you to kind of look at them and see what's going on. Another possibility is to show them simultaneously. For example, you can activate frame, a standard graphics option, so that you put projected coordinates on the border and you use geo-axis. So you have unprojected coordinates here, right? So that is a very easy and nice ways to distinguish the two types of coordinates. So we can do this for other projections. For example, imagine that we have a map of the world now in the Lambert azimuthal projection. So we still have the geo-axis here, and now we also turn on the geogrid lines. So this is 15 degrees, 30 degrees, 45, 60, 70, 90, and now here we have the pole here, because in this projection we can see the whole world at once. We can use these for any region of the world, and we can also style the geo-axis. For example, here we are saying that the axis itself is going to be white, and here we are also giving indications of how we want to style the ticks. So they will have Halloween, etc. Also, this is the other option I was talking about. We can select where is the origin, right? By default, it will be the 0, 0, but we can also select that we want the origin, our geo-axis to cross at our location here in Champagne. Again, let me finalize this section by emphasizing how different the maps are when you use different projections, right? So for example, here we have the rectangular projection for Svalbard, and you see how the geo-axis coincide with the axis. but the shape is very deformed. These two other projections are much more respectful with the shape of the island. And now we have, again, these are the geo-axis. We see that they are at latitude around 79, 80, 78 to 80. And look at the projected coordinates for the Mercator projection. We can also use the Lambert azimuthal projection that we used before. The shape is fine. Here we see again 79, 78, 79, 80. But now the projected coordinates are in radians, because that's how this projection works. So you see how the same area can look very different from a projected point of view, but the geo-axes are always going to be showing you true latitude and longitude. Okay. That's all for geo-axis. Let's move on to the new updates about these three geoprimitives, which have the characteristic that they depend on time. So the first extension is that they now have a new option called reference altitude that has been inherited from the function sunrise and sunset. So for example, if we evaluate this, I'm going to evaluate again. So this is now showing the night hemisphere, the part of the Earth which is currently in darkness and night, and this is the part in daylight. So, and you see every time that you evaluate it, it will be different because it depends on time. You can put here the time that you want. Now, the new thing is that we have added the reference altitude, which takes either a number in degrees or these standard named values for twilight. So by default, night hemisphere separates the Earth in two equal area parts. But with civil, what we do is that we push 6 degrees the horizon down, 12 degrees for the nautical, and 18 degrees for astronomical. So with this, it means that we really want a very dark night to do astronomical observations. And so these are the three ones, the four, the original one plus the three one. And here we have a manipulate in the orthographic projection in which it's much easier to see what's going on, right? So here we control the center of the globe. And here you see how the original one is here, which is separating the Earth in two parts. This is 6 degrees from this one, now 12 degrees, now 18 degrees. And this is dark enough for astronomical observation. Okay, so that's one of the extensions of these primitives, the new option reference altitude inherited from the astronomical functionality. The other extension is that now these functions can work on other bodies. For example, we take it now, so that's our date right now, and so we are going to use that date, for example, to show the face of the moon with the moon center still at 0, 0, right? So this is more or less the face. I mean, this is exactly the face of the moon that we would see if we looked at the moon. Now, what we are going to do with a manipulate is to do exactly the same thing, but now we will be varying time. So now date varies a so-called synodic month, which is 29.5 days. That's a full cycle of phases of the moon. So let's do that, and we see what happens. Right? Notice that there are several effects going on here. First, because the moon is on an elliptic orbit, sometimes it looks bigger, sometimes it looks smaller. We see the face, and also, again, because the orbit is elliptic, it seems to wobble. It's not that we always see exactly the same face of the moon. We see like 56% of the moon, right? Because sometimes it shows a little bit here, sometimes a little bit more there, right? So this wobbling of the moon is called libration. Okay, we can do that now for any other body. Let's take Venus, right? So this is exactly the same thing, the current phase of Venus. So the sun is on this side, illuminating Venus. And here we have to do some computation because the equivalent of the synodic month is not so famous for the moons, so for Venus, sorry. So we do same computation. And now we see how the same effects, because Venus changes distance with the Earth by a lot, we see the same effects, but kind of exaggerated, right? So we see the phases. Also notice something interesting in Venus, which is the only planet that rotates backwards. It's rotating towards the left, while all other bodies in the solar system rotate towards the right. So you see how much information we can see in one of these plots and manipulates, etc. My colleague Jeff Bryant would remind me that Venus is full of clouds, so the realistic picture is to show like this part fully white, because we don't see the surface of Venus like this. We see only clouds. So yes, that should be fully white, realistically. Okay, that was the second part. Let's now go to the third function I wanted to show. This is a new function. We have had solar eclipse for many years, and it was overhauled a few years ago in 2024 and for version 14. So this new function is able to find solar eclipses for a given location. So by default, if you give a location, it will find the next umbral, meaning total, annular, or hybrid eclipse that will cover whose path of totality will cover that location. And for Champagne, seems to be in July of 2093. Eclipses, total eclipses or umbral eclipses happen rarely, every 100 years or so for a given place. So that's kind of in the average. So which type of eclipse will that be? For that, we have to now query solar eclipse, and it says it will be an annular eclipse. We can draw a map of the envelope of the umbra, so that's the totality path, and we see that Champagne is at the very beginning, so the sun is going to rise on that date already eclipsed. Yep. So let's do the same thing for London. And now let's be specific and say that we really, really want total eclipses only. So the next one is going to be in 2151. We can compute the same totality path and plot it on a map. And we get that map. And you see it goes through London. In this projection, it looks kind of tilted, but we can have another map of the same geopolygon. We add a geomarker at London. We say that we want a range centered at London and with a range of 200 miles. So the distance from here to here is 200 miles, right? And we see how London is indeed in the path of totality. We can do something like, what was the previous eclipse? So time direction goes to the past. The previous eclipse that went through Champagne, and that was 1869. Or we can say, give me all the eclipses in the interval of years between minus 13,000 and 17,000 that go through Champagne. Right? The Wolfram language has very precise ephemerides data from NASA, essentially between these years. And so it has tabulated the 72,000 solar eclipses in this range, and it's able to do computations with the polygons quite fast. So you see, it solves the whole problem in 7 seconds. So these are all the eclipses. There are 201. And if we ask for types, we see that there are 74 total eclipses, 124 annular eclipses, and 3 hybrid. Hybrid eclipses are those that start annular, they become total for some time, and then they become annular again. So they change during the process of the eclipse. They change type between these two. Okay, so that was 4 points. Like you give a geoposition anywhere on Earth, and you get all the information of eclipses for any of those 30,000 years. Now, let's do the same thing for extended location. So now here, there is a non-trivial geometrical computation problem of intersections of lots of polygons. So that's going to be the next total eclipse on the US, 2044. And here is a map of it. And you see how the path of totality of the eclipse actually, indeed, intersects with the polygon of the US at the end. So we can also ask things like, what are the eclipses that are going to be visible from Spain in the next 3 years? And this is a rare situation in which in 3 years we have 3 eclipses. So this is going to be, this one is going to be this August 12th, and then there will be another one, and then another one, all in a period of like 18 months. So that's quite unusual. We can do things like find all the eclipses the US in the last 100 years. We get 17, and we can show them in this map with tooltips. Here I added some tooltips. And for example, this was the famous eclipse of 2017. And this was the eclipse we had a few years ago in 2024. And you see how some eclipses are thinner, some others are thicker. Typically, this means these are annular. The thinner ones are the total ones. And this one, for example, ends in just touching the little bit of the US, right? But we find it, right? We do the geo computation, and we find it too. And then, as a final example, let's get all the eclipses through Costa Rica in 10,000 years and plot them in this map. And you see how we get this kind of butterfly figure of all the totality paths that go through, that intersect Costa Rica. There. So 229 different eclipses. And I'm going to finalize by mentioning another extension of the solar eclipse functionality, which is support for a different type of eclipse type. So the traditional nomenclature for eclipse types is total, annular, hybrid, and partial, right? So 4 types. Muse, an astronomer from Belgium, I think, invented a new classification based on geometric configurations, and he has 7 types. And the 7th type is quite interesting because it's a configuration in which the shadow cone from the moon touches the Earth, but the axis of the shadow cone does not. So the shadow cone only touches barely, and in a very close to the poles region. And what happens if we find, for example, the next eclipse of Muse type, which is going to happen in 2043, we can check that it's umbral, so it will have a path of totality, but it's not central. The axis of the shadow cone will not touch the Earth. And so what happens is that the path of totality has this small and funny lenticular shape, right? So it's only in a very small area the eclipse will be visible. Okay, so that's all about eclipses. Let's now go to the final section I wanted to talk about, which is orbital elements. First of all, let's talk about what orbital elements are. So imagine that you have an orbit, say a satellite around the Earth, a planet around the Sun, anything, an orbit. And so to describe the shape of the orbit, we need 2 numbers. Imagine the 2 semi-axes of if the orbit is elliptic. Then we need 3 numbers to define the orientation of the orbit. And finally, once we have the orbit defined by these 5 numbers, we need 1 angle to say where the orbiter, the planet or the satellite, is on the orbit. So for example, these 2 first ones, this is a size, right? So it increases the size of the orbit. This increases the eccentricity. Recall that if the eccentricity is 0, this is a circle. Between 0 and 1, it's an ellipse. At 1, it becomes a parabola. And beyond 1, it becomes a hyperbola. But you can have eccentricities beyond 1, right? Okay, so let's use something like that. Now, those 2 numbers define the shape and size of the orbit. Now, the orientation is defined by inclination with respect to our plane, which is, for the solar system, it will be the ecliptic plane. Then we have the longitude of the ascending node. That point over there is the ascending node. So we are looking at this green angle. And then finally, we have the so-called argument of periapsis, which is just moving the ellipse on a plane. And that's the blue angle. And finally, once we have the orbit where we want it, we have the so-called anomaly, which is the angle from the semi-minor axis to the position of the orbiter. Right? So we need those 6 numbers to define the position of the orbiter. Think of them as equivalent to position and velocity vectors. So 6 numbers. We are going to add 2 more, which are the date we are doing the computation and the mass of the central object. So we will be working with 8. So let's look at some examples. For example, Ceres, the asteroid Ceres. So if we ask for, sorry, that's our body, and that's Ceres. So we have the periapsis distance, the eccentricity, the inclination. You see all the 6 numbers we used before. We are going to use a different type of anomaly, but it's equivalent, an angle around the focus of the orbit. And then we give the date when we did this computation right now. And this number, which is equivalent to the mass of the total system, essentially the mass of the sun. We can compute an individual orbital element. We can compute lists of orbital elements. And you see, every time I evaluate this, they will change because these things depend on time. And then if you just say all, you get a long list of many things that you can compute about the orbiter. We have right now 56, but there are many things. Some are there are vectors, velocities, various forms of distances, when will we have the next periapsis or apoapsis, etc., etc. Lots of different things. And 2 of them are a time series in case you want to compute many more positions very fast, or an orbit line. Something that I wanted to mention here is that these are so-called osculating orbital elements. And that means that they are computed instantaneously. And for example, the Earth keeps going up and down because of the pull from the moon. And the eccentricity is not constant. It changes because of the pull of the moon, right? This is monthly variations. If you now compute the same thing for the Earth-Moon barycenter, the barycenter of the 2 bodies, that's a lot more stable. This is a very, very stable value in comparison with the oscillation of the eccentricity of the Earth due to the pull of the moon. These are things that you can compute very fast in microseconds. So they are very good for applications. Okay, let's work with some other examples. For example, something very trivial now is to plot a model of the solar system. That's it, right? And you see how nearly all of the orbits are in the same place. It's not exactly the same place. There are variations of about 1 or 2 degrees, but that you have all the bodies, right? So the 4 internal bodies, and then Jupiter, Saturn, Uranus, and Neptune. Let's look at GPS satellites. This is fun. So we take, we ask Wolfram Alpha about the list of all the GPS satellites. We compute orbital elements for all of them. So this is a list of associations. Remember that the orbital elements were given as associations. We can put them in a tabular object. That's very nice to read. You see that with the units, and this is very nice. Dates, etc. And for all the 20-something satellites, sorry, 54 satellites. And now we compute orbit lines. We construct a really trivial model of the Earth as a blue sphere, and now we can put them in a manipulate, and you see the motion of all the GPS satellites over a day. And if we construct a little bit more complicated model of the Earth, we can do something even nicer. You see how they move, sorry, how they move, and at the same time we can rotate the Earth, right? So you see how easy it is to construct models. So you see how there are no polar satellites. They are all distributed around the Earth. Yeah, it's very easy to construct. Let's do the same thing for the moons of Jupiter. We get all the moons, which are 95. we construct again a trivial model of Jupiter, and now we can very easily have the orbits of all the moons of Jupiter. And notice here these ones, which are the inner moons, which are precisely the Galilean moons. If we do if we zoom over there, we get this little solar system that includes the 4 satellites that Galileo discovered. So this is, so let's see, this is Ganymede, Europa, Io, and one of these is Callisto. Well, okay, and then the final example is just to show you that we can use orbital elements with anything. This is Voyager 2. So we can construct the current orbital elements of Voyager 2. We construct the orbit line from it. This is a line object. And now we construct an orbit asking astroposition for the true orbit that Voyager 2 had over the years. And we get these two things. We get a graphics that contains simultaneously here the bodies of the solar system, the true orbit of Voyager 2, and the current orbit of Voyager 2, right? This is again a 3D graphics, right? And so what happens here, we can zoom in, is that we see how Voyager 2 used the assists by Jupiter, Saturn, Uranus, and Neptune, and then at the very end, it took this hyperbolic orbit, right? And now it's there. You see how far it's getting from the solar system. And it's a hyperbolic orbit because the eccentricity is much larger than 1. It's clearly a hyperbolic orbit. Okay, so you see that with orbital elements, there are very many things that can be done already, but we want to do more things. So I have here a few plans for 15.1. We want to create a new object that by itself will know everything about orbits. This is, it will be renamed perhaps, but that's an object that will be understood by astrographics and other astrofunctionality. And then something I didn't mention is that those satellites actually must be propagated with more care than we do right now. Right now, we only use Keplerian orbits, but in the future, we need to use the effects of Earth dragging, the resonances with the rotation of the Earth, and the pull from other bodies, mainly the Moon. There is a standard way of doing that. It's called SGP4, and that's something that we'll be adding for the next release of Wolfram language. And that's all from me. I will have a look at questions if there are questions. Now, let's see. Gloria asks, does the time default if not entered? I guess this is about night hemisphere. And yes, so for example, if we do here, this is equivalent to doing now. Right? So now some time has passed, so you see it moved a little bit, but yeah, having no argument is equivalent to now. It is hard to understand the rotation of Venus without reference positions. Yes, I understand what you mean. It's the rotation with respect to us looking at Venus. Yes, but the astrofunctionality has a lot of different reference frames, including the International Celestial Reference Frame, the ecliptic frame, the equatorial frame. So if you want to use a particular frame to observe the rotation of something, then yes, it's possible to do that. Yes, yes, there's a question here from David. When I evaluated the notebook, I got a curved line from, yeah. So this is I realized I was testing other things, and what I had is, instead of line, I had geopath. This I was testing thing, and then a geopath is a geodesic, and it looks very different, right? So a geopath is a geodesic on the surface of the Earth. A line is a straight line on the map. And of course, it will cross different points depending on the projection you are using. So yes, I did notice that while reviewing the notebook, and I changed from geopath to line. what about the case in which one would like to create their own solar system? Yes, so orbital elements has also a notation in which you can provide the mass of all objects and the initial orbital elements of all objects. And then orbital elements will do the predictions of positions and velocities for you later on. So yes, you can create your own solar system as well. David, yes, first time I've seen the astronomy capabilities. Amazing to me. Thank you. Yes, there are lots of things that can be done. And remember that they are all based on the most recent ephemeridis data from NASA. So it's super precise and covers 30,000 years of time for the whole solar system. Can you predict potential collisions? Well, we have the data, but we would have to use a function called find astro event. You can use that function to find the dates of closest approach from different bodies. So if you suspect that two different bodies are going to get very close to each other, you can ask for that function for when they are going to be closest to each other, and then you can check whether that distance is smaller than the sum of the radii. Okay, so I have a few more minutes. What is the standard format for entering data for a satellite not included in the Wolfram database? Okay, so there are two different ways to do this. One is an association of orbital elements. So let me go again back to this. So, for example, if you can create your own association like this one, and once you have this association, like we ask about series, right? We can take those ones and ask for another property. Like, for example, here we were given the mean anomaly, but you want to say, no, I want the true anomaly. Well, I have it here, anomaly, right? So it's going to give you the value computed from this. So if you had added like a sun of a different mass here, this is equivalent. This is the gravitational constant times the mass. So then you would get a different solar system, right? With different radii and different velocities, etc. The other method is to use TLEs. If you can get a TLE, which is a two-line elements from about any satellite, that's the standard way of giving information about the satellite, you can also put it in the first argument of orbital elements. Let's see. Is there any support for custom global grids like Python, Alphin's Pilot, Exasphere? I'm not sure what you mean by this. I think you may be thinking of these models of the Earth based on like subdividing a polyhedron. We don't do that yet. Can you simulate a rocket from the Earth to the Moon? That's another thing we are working on. We don't have yet computations of our own orbits with engines, but we are working on that. You should give a copy of Mathematica to Andy Weir. yes, that he certainly he should use our functionality. So that means the events are actually calculated, but rather listed in a table. No, what the NASA provides is ephemeridis data. So it means it's a bunch of Chebyshev coefficients. It's a bit like a Fourier transformation that describes the orbit. But then the computations of the closest distance and things like that, those must be computed. The important events are not tabulated. They just give the orbits. Can we compute orbital elements of comets? Yes, of course, totally. In Wolfram language, we have lots of comets, and we have orbital elements for all of them. Yeah, you can work with all of these comets. Yes. So James Cobb is asking about all their computations that were very slow. Indeed, in the past, we were contacting Wolfram Alpha to do these computations, but now Wolfram language itself has all these computations performed locally, very efficiently in microseconds, and it's all a lot faster than it used to be. And I think last question, can version 15 implement hover tooltips on interactive 3D surface plots similar to Plotly? We have in the Wolfram function repository some 3D visualization functions about astronomy. I would recommend you to check them. They allow having tooltips there. And the last question, are there options to specify universal transverse Mercator or state plane coordinate system? Yes, we do have all the 60 UTM projections and the several hundred state plane coordinate systems. Actually, we have those of the 1927 and those of 1983. We have all of them. Okay, so I will conclude here, and yeah, thank you, and I will stop.
Thanks, Jose. Those are such beautiful images on those geographic and astronomy calculations. I want to remind everyone, thanks for sticking with us and joining us today. Next week, our topic is mathematical computation, and we have a number of intriguing topics to cover with a number of our more of our Wolfram developers bringing their expertise. And the following week on Thursday, we will focus on notebooks and the new AI assistant and new visual themes and more notebook technologies. So hope that you will sign up for these individual sessions, or even if you sign up for the series here, you will automatically be signed up to get reminders about these upcoming webinars. So I encourage you to do that. Thanks everybody for your attention. Please answer our survey. It's pinned at the top of our chat pane, and